We present OReX. In this paper, we use neural fields to reconstruct 3D objects from sparse collections of 2D slices. Our method is able to produce quality meshes with high-frequency details on variety of modalities and slices orientations. Our key idea is to use neural field to interpolate between the input slices. Our pipeline starts with sampling points on the slices, then training a neural occupancy field on those points, and finally extract a mesh from that field. Baseline implementation of this pipeline using regular grid sampling and a basic MLP as the neural field yields overly smooth results. This smoothing is a result of spectral bias and is the main challenge in this work. Our method improves each part of the pipeline to reduce this bias. The first improvement is the introduction of frequency-aware sampling. We reduce the spectral bias by focusing on the important regions, sampling points around the boundary. We also sample points uniformly from the convex hull and slices for stability. Boundary points are resampled with increasingly tighter distributions throughout the training to gradually expose the network to higher frequencies. Our next improvement is to the network's architecture. Our base unit maps 3D coordinates to occupancy levels using a residual network. We use the base unit recursively to gradually refine a guess and output the final occupancy level. This allows the network to perform smaller scale corrections and learn finer details. We visualize the refinement progression by coloring grid points based on their occupancy level after the first and last refinements. All the corrections in red and blue are at the shape's boundary and mainly at regions of high frequencies. Smoother regions remain stable. Our final contribution is removing artifacts in the extracted mesh. In the final phase, we use Marching Cubes algorithm to extract the mesh. The resulting mesh has wave-like artifacts due to the snapping of vertices to the grid points. The snapping is a result of high field polarization induced by the binary cross-entropy loss. We alleviate these artifacts by limiting the gradients of the field using hinge-like regularization. Adding the regularization yields smoother fields, natural distribution of the vertices, and smoother reconstructions. We compared with recent reconstruction methods using three metrics: Hausdorff distance, intersection of a union in 3D and 2D. The qualitative and quantitative comparisons show we surpassed the state of the art. This X-ray view shows our method's ability to capture complex internal geometries such as cavities and tunnels. Our usage of neural fields as our interpolation prior allows learning from global shape information. In this demonstration, we reconstructed two variations of the same general shape, round and sharp. The neural field uses self-similarities and global shape information to extrapolate the top of the snot with a style consistent with the general shape. Since our method imposes very few restrictions on the input, the neural field is able to handle unknown regions. In this example, our method successfully extrapolates the pink region based on global information. Thank you all for your attention. We hope you enjoyed.